Hey everyone, welcome to Simplilearn's YouTube channel. In this session, we will be learning about trees in data structures. But before we begin, let me tell you guys that we have daily updates on multiple technologies. If you're a tech geek in a continuous hunt for latest technological trends, then consider getting subscribed to our YouTube channel and don't forget to hit that bell icon to never miss an update from Simplilearn. Now, without any further ado, let's get started with the agenda for today's session. Today we will be discussing trees in data structures. So first, we will understand what exactly are trees in data structures. Followed by that, we will understand the first type of trees in data structures, which are the binary trees. Then, moving ahead, we will learn the binary search trees in data structures. Followed by that, we will learn the AVL trees in data structures. Next, we have B trees in data structures. And finally, we will wind up the session by discussing B+ trees in data structures. Hope I made myself clear with the agenda. Now let's get started with our first topic. Over to our experts.
So we will be discussing what exactly is a tree data structure. Followed by that, we will understand why we need a tree data structure. Then we will learn the tree terminologies. Followed by that, we will understand tree node. Then we will see the types of trees. And followed by that, we will understand the tree traversal. And finally, we will see some applications of trees in real time. I hope I made myself clear with the agenda. Now, let's get started with the first topic, that is, what is a tree data structure? So what exactly is a tree data structure? The tree is a non-linear data structure that consists of nodes and is connected by edges. I know it's a little difficult to understand just by the definition, so let me show you the pictorial representation. As you can see, we have the elements, that is 10, 20, 30, 40, 50, 60 and 70, and all these are stored in the tree data structure. They are stored in a non-linear structure. If we had used arrays, it would have been in a linear consecutive way where 10 starts first and 70 ends at the last position. Now, in the next section, we will discuss why we had made to a switch to the tree data structure when we already had a linear data structure, that is array. Now the next topic, that is why we need tree data structure. So there are many reasons why we had switched into tree data structure, and one of the reasons is a linear data structure always stores the elements in a sequential form, that is, one after the other. And in operations to be performed in linear data structure, the time complexity increases as the data size increases. You can see here that, as discussed before, the elements are stored in a linear form, that is 10 at the first place and 70 at the last place. Imagine you wanted to access the element 70. Then using the traversal, you had to start from the first position, that is 10, 20, 30, 40, and slowly at the end is 70. So accessing that particular element is really time consuming. We are facing this just for 70 elements. Imagine if we had 700 elements, right? So that is exactly why we had made a switch to tree data structure. And using tree data structure, we have many advantages, as the tree data structure is completely non-linear and it allows easier access and quicker access of the data elements. How is that possible? We will look into it into the next segment, where we will discuss about the traversal of trees. Now, before we understand the traversal of trees, we should understand another important topic, that is the terminologies of tree. So the first one is the node. Node is the entity that contains the keys and pointer to its child nodes. So here you can see that the elements A, B, C, D, E, F and G are the elements. So each and every element, or the blue dot, is called as a node. And the blue dots here are 1, 2, 3, 4, 5, 6 and 7. So we have 7 blue dots. So we have 7 elements here. So you can see the line between each elements, right? So this particular line is called edge. Now we'll discuss about the edge in the next part. So the connecting links between any two nodes are called as edges. So we discussed about the nodes, right, where the element is stored. The blue dots are the nodes, and the lines connecting between the elements or nodes is called as the edge. So out of all the nodes, this first node, that is the element A, is called as the root node in a tree data structure. So indirectly, root node is also called as the parent node of all the nodes. Now we will understand what are parent nodes and children nodes. So in a tree data structure, the node, that is the node's predecessor, is called as parent node. So here we have discussed that A, or the root node, is the parent of all nodes. So for A, B and C nodes are children nodes. And for B and C nodes, A happens to be the parent node. Similarly, D and E are the children nodes of B, and F and G are children nodes of C. And the nodes D and E have B as the parent node, and the nodes F and G have C as the parent node. Now followed by that, we will understand the descendant node. So as discussed before, the descendant node is the node that comes after the parent node. Here, the B and C are the descendants of A, and D and E are descendants of B, and similarly F and G are the descendants or children of the node C. So in a tree data structure, the node which does not have any child is called as the leaf node. Now at the end we have D, E, F and G. So these particular nodes do not have any children nodes like B and C. So these particular 4 nodes which do not have any children are called as the leaf nodes. In a tree data structure, the node with at least one child node is called as the internal node. So here the internal nodes are B and C, which have at least one child. In a tree, the total number of children of a node are called as the degree of that node. So in this particular diagram, the degree of a root node is 2 because it has 2 child nodes, and the degree of B is 2 as it has 2 child nodes. Similarly, the degree of C is 2 because it has 2 child nodes. But when it comes to D, E, F and G, the degree is 0 because they do not have any child nodes. In a tree data structure, the root node is said to be at level 0, and the children of the root node are said to be at level 1, and the children nodes of the level 1 are at level 2. So to understand this, let's go through the diagram. As you can see, this particular root node is called as level 0. And followed by that, we have the children nodes of A, that is B and C, and that level is called as level 1. And followed by that, we have level 2. And if this tree goes forward, the levels also increase accordingly. Now, in a tree data structure, the total number of edges from a leaf node to the particular node is the longest path, and this particular path is called as the height of that node. Now here we have our general tree data structure, and here you can see the height of node A is 2. And the height of node B and C together is at 1. And the height of the last leaf nodes happens to be 0. Next, in the tree data structure, the total number of edges from the root node to a particular node is called as the depth of that node. Now in this particular tree data structure, the depth of the root node is 0. And the depth of B and C together is 1 because the number of edges connecting to the node A from B is just 1, and similarly the number of edges connecting the node C from A is just 1. So the depth of both B and C is 1. Now if we consider the last leaf nodes, then the depth is 2 because if you see, G is connected to A using 2 different edges. Similarly, F is connected to A using 2 different edges, and E and D also have 2 nodes to connect to A. So the depth is 2. Now in the next segment, we will understand the tree node. So the tree data structure has data part and references to its left and right child node in the tree data structure. So here you can see this is the node, and the node has 3 segments, that is data element and the references to its left child and the references to its right child. Now there are 4 different types of trees. The first one is the binary tree. Followed by that we have the binary search tree. Then we have AVL tree. And finally we have the B tree. Let us discuss each one of them. The first one is the binary tree. A binary tree is a tree data structure in which each parent node at most has 2 children. So in this particular tree, we'll have at most 2 children. That means it might have 1 or more than 1 but not more than 2 children per node. Moving ahead, we have the binary search tree. So a binary search tree, or a BST, is a tree data structure in which each node has a maximum of 2 children. All nodes of the left subtree are less than the right node. All nodes on the right subtree are more than the root node. So here you can see the image, or the GIF, which represents the image of a binary search tree. So here, all the nodes of the left subtree are less than the root node, and all the nodes of the right subtree are more than the root node. The next type of the tree is the AVL tree. The AVL tree got its name after inventor George Adelson Welsky and Landis. AVL tree is the self-balancing tree in which each node maintains a balance factor whose value is either 1, 0, or -1. Balance factor is equals to height of the left subtree minus height of the right subtree, or height of the right subtree minus height of the left subtree. So in this particular image, you can identify it as an AVL tree. And now the last type of tree, that is the B tree. B tree is a special kind of self-balancing search tree in which each node can contain more than one key and can have more than 2 children. B tree is also known as the height-balanced M-way tree. Now in this particular GIF, you can see how a B tree looks like. Now followed by this, we will discuss the tree traversal. So traversing a tree helps to visit required node in the tree to perform specific operations. Tree traversal can be performed in 3 different ways. The first one is the pre-order traversal, where we visit the node and visit all the nodes from the left side, then visit all the nodes from the right side. So this particular GIF is an example for pre-order traversal, where we visit all the left side nodes first, then we visit the right side nodes. Now we will move ahead into the next type of traversal. That is the in-order traversal. First, we visit all the nodes from the left side, then we visit the root node, and then we visit all the nodes from the right side. So this particular GIF will be an example for the in-order traversal, where we visit all the left side nodes, then we visit the root node, and followed by that we will visit the right side nodes. And the last type of traversal is the post-order traversal, where we visit all the nodes from the left side first, then we visit all the nodes from the right side, and finally visit the root node. So this particular image on the right side is an example for post-order traversal. Now before we get into learning the applications of trees, we will try to execute one example based on the post-order, pre-order, and in-order traversals in tree data structure. So you can see that we have an example on my screen right now. So here we have the node structure, then we have the in-order traversal function, followed by that we have the pre-order traversal function, and finally we have the post-order traversal function. Now let's quickly run this program and see the output, and don't worry about the code. This particular code document will be attached in the description box below and you can have access to it. Now we have the run option over here and the program got successfully executed. You can ignore this warning, and here we have the in-order traversal of the tree and the first output. Then we have the pre-order traversal of the tree, and finally we have the post-order traversal of the tree. Now let's discuss the last part, where we will learn the application of trees. So the application of trees are as follows. Binary search trees are used to quickly check whether an element is present in the set or not. Then we have the most popular database usage of B tree, which is a variant of tree data structure. Then we have the modified version of trees called as trice, which is used in the router to store routing information. And finally, the compiler uses a syntax tree to validate the syntax of every program you write. So we shall begin our session by learning a binary tree and some basic terms related to binary tree. Then we will try to implement it in the code editor. After that, we will discuss its properties. Then we will discuss different types of binary trees. Then we will try various operations on them like traversal, insertion, and deletion. And finally, we will take a glance on what are our final key takeaways from this session. But before we begin, make sure that you have subscribed to our YouTube channel and clicked on that bell icon to never miss an update from Simplilearn. So without further ado, let's get started with our first topic, that is, what exactly is a binary tree? So it is a tree data structure in which each node can have at most 2 child nodes. These nodes are referred to as left child node and right child node. Next, let's discuss about some terms related to binary tree. First up, a node. A node consists of data and a link to its both child nodes. Next, the root node. Root node is the first node of the tree. Next, leaf nodes. These are the nodes which has no child. Next, parent node. Apart from the root node, any node which has at least one child is called as parent to that child node. Next up, a child node. Any node with a parent is called as a child node. Next up is the internal node. Any node with a child and a parent is called as an internal node. Next up is the height of the binary tree. The longest path from the root to any leaf node is called as the height of the binary tree. Next up is the depth of the binary tree. The depth of the node is the total number of edges from the root node to the target node or the last child node. Now let's try to implement the binary tree in the code editor. As you can see, now we are on the code editor, and the code on my screen is an example for binary tree. Now here you can see that we have created a structure for node, followed by that we have a function where we will print the tree, and this is our main function. Now don't worry about the code, this particular code segment will be available in our description box below, and you can always have access to it and try to edit and run this code on your own local system to have a better learning experience. Now without further ado, let's try to run this program quickly and see the output. So there you go, the code got successfully executed, and here you can see the output of this particular binary tree. Now let's get back to the theory part. So as discussed before, followed by the implementation part, we will learn about the properties of a binary tree. Now let's discuss the properties of the binary trees. First up, maximum number of nodes at a level L is 2 to the power L. Next up, maximum number of nodes in a binary tree of height h is equals to 2 to the power of h minus 1. Next up, minimum possible height in a binary tree with 2 nodes is equals to log of L plus 1 base 2. Next up, the minimum possible level in a binary tree with n nodes is equals to log of L plus 1 base 2. Finally, a binary tree with L leaves has at least log L base 2 plus 1 levels. Now, let's discuss about the different types of binary trees. First up, we have the full binary tree. Followed by that, we have the complete binary tree. Then we have the perfect binary tree. Followed by that, we have the balanced binary tree. And lastly, the degenerate binary tree. Let's discuss about these in detail. First up, full binary tree. A full binary tree is a unique tree data structure in which a node can have either 2 children or no child. Next, a complete binary tree. So a complete binary tree is another specific binary tree where each node on all levels except the last level must have 2 children, and at the lowest level, all leaves should reside possibly on the left side. The next one is the perfect binary tree. A binary tree is perfect if every node must have 2 children and every leaf is on the same level. The next one is called as the balanced binary tree. A binary tree is balanced if for each node the height of the left subtree and the height of the right subtree varies at most by just 1. At last, we have the degenerate binary tree. A binary tree is said to be degenerate if every internal node has only one child. We have now discussed the binary tree, some terms and properties related to binary trees, and types of binary trees. Now we will look into the operations that needs to be performed on the binary tree. So there are basically 3 types of operations that can be performed on binary tree, which are traversal, insertion, and deletion. So first we'll look into the traversal operations.
There are three different types of traversal operations possible on binary tree, which are pre-order traversal, in-order traversal, and finally the post-order traversal. Now let's get back into the text editor mode and try to execute our example. So right now we are on the text editor, and this particular code is for the traversal operations on our binary tree. And here you can see we have the structure for node, and we have also the in-order function, pre-order function, and post-order function. And don't worry about the code. This particular code will be available in the description box below. And after you have written the code, we have some standard input over here. You can see that we are giving the number of edges as 4, and the left subtree elements are 2 and 1, and the right subtree elements are 2 and 3, and another left subtree elements are 3 and 5, and lastly we have 5 and 6 for another left subtree. Now let's try to execute this code. Now we have already executed the code, and we also have the output over here, and here you can see we have entered the number of edges as 4, and the traversal is in-order traversal, which is 1, 2, 6, 5 and 3, and the pre-order traversal output is 2, 1, 3, 5, 6, and the post-order traversal is 1, 6, 5, 3 and 2. Now let's get back to the PPT. Now we have the insertion operation. And now let's get back to our text editor and try to see an example for insertion operation as well. So on my screen you can see an example for insertion operation. So here we have the insert function. As I said, this particular code will be available in the description box below. Now let's provide the standard input. So the standard input will be 4 edges, and we have 2 and 1 as the left subtree, and 2 and 3 as right subtree, 3 and 5 as left subtree again, and 5 and 6 as the left subtree. Now let's quickly run this code, and there you go, the program got successfully executed, and here we have the output. The nodes got inserted, and it has provided an in-order traversal, that is 1, 2, 6, 5 and 3. Now let's get back to the presentation, and the last type of operation is the deletion operation. Let's quickly execute an example based on deletion operation as well. Now as you can see, we are on the text editor again. Now here the example is for deletion operation. We have the delete function over here. Now for this particular program we don't need any standard inputs, so just let's run the program. So there you go, the program got successfully executed, and we have the output over here. And in order traversal before deletion, and in order traversal after the deletion of an element. So the deleted element is element 11. Now with that, let's get back to the presentation mode again. So that's how the element got deleted. Now we have reached to the last part of this session, that happens to be the final key takeaways. So what are the final takeaways? So binary tree is faster at search operations than other type of tree, and it is easier to find maximum and minimum elements in the binary tree. Binary tree does not allow duplicate values, and graph traversal is done using binary tree. It is used to convert the postfix expressions into the prefix expressions.
We shall begin by introducing binary search trees. Then we will discuss some of the properties of binary search trees. After that, we will try various operations on them like insertion and deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below, so you never miss an update from Simplilearn. So without any further ado, let's get started with introduction to binary search tree. Binary search tree is a set of nodes organized in such a manner that they all have the same binary search tree characteristics. A key and a value is assigned to each node. The requested key is compared to the keys in binary search tree. So during search, if the key is found, then the corresponding value will be retrieved. Next up, properties of binary search tree. First up, the left subtree of a node contains only nodes with keys lesser than the parent node. Next up, the right subtree of a node contains only nodes that are greater than the parent node. The left and the right subtree each must also be a binary search tree. Next, let's discuss what are the operations we can perform on a binary search tree. First up, insertion. Last, deletion. Let's discuss them in detail. First up, insertion. We can insert a node in such a way so that we obey binary search tree rules. That is, the new node should be either less than the parent node if it's on the left subtree, or if it's on the right subtree, it should be greater than the parent node. Let's execute this in the code editor. We will start by creating a class for the binary search tree. So class bst int data and bst pointers left, comma, right. Next, we will define some functions publicly. Public first default constructor, and a parameterized constructor. A function to insert the value. And a function to traverse the node. Now let's write default constructor's definition. So bst Now let's write the parameterized constructor's definition. Bst int value data is equals to value and left is equals to null and right equals to null. Now let's write the definition for the insert function. So bst insert bst star root comma int value. Now we will check if the tree is empty or not. So if root, then we will insert the first node. So we will return new bst value. Otherwise, we will insert the data. So if the value is greater than root data, then we have to insert it in the right subtree. So root right is equals to insert root right comma value. Else the value should be inserted in the left side. So root left is equals to insert root left comma value. And then we will return root. Now let's write the traverse function. So void bst traverse bst star root. If root then we will return otherwise we will first traverse left side, then we will print the root data. And then we will traverse the right side root right. Now let's write the main block. So we will start with an empty tree. So bst b comma star root is equals to null. The root is equals to b dot insert root comma 50. B dot insert equals to root comma 10. B dot insert gonna be root comma 30. B dot insert gonna be root comma 50. Sorry, we already use 50, so we will use 60. P dot insert root, comma, let's use 20. Let's try to traverse this. So B dot traverse root. Let's execute this. As you can see, we have successfully created and traversed our first binary search tree. Let's get back to slides. At last, deletion. We will delete a node following the binary search tree rules. That is, the value of the left subtree should be less than the parent node, and the value of the right subtree should be greater than the parent node. Let's try these in the code editor. Let's start by creating a node. This time we will use structure. So struct node int key struct node star left comma star right. Now we will create a utility function to create a new binary search tree node. So struct node star new node int item. Struct node star temp equals to struct node star malloc size of struct node. Next, temp will be assigned the key is equals to item. Temp left equals to null and temp right is equals to null. Now let's write a function to traverse the tree. Traverse struct node star root. So if root is equals to null, so traverse root left cout root key traverse root right. Now let's write a utility function to insert the new node with the given key in the binary search tree. So struct node star insert struct node star node comma int key. So if node is equals to null, then we will return new node key. Otherwise, we will recur down the tree. So if key is less than the node key, then we will insert in the left subtree. So node left is equals to insert node left comma key. Else node right should be inserting key. Now let's return the node. Now we have given a non-empty binary search tree, so we have to return the node with the minimum key value found in that tree. So we will start struct node star min value node struct node star node struct node star current is equals to node. So we will loop down to find the leftmost leaf. So while current and currents left is not equals to null, so current should be equals to current to return current. Struct node star delete node struct node star root comma int key if root equals to null, return root. Now, if the key to be deleted is smaller than the root's key, then it lies in the left subtree. So we will check if key less than root key, then root left will be equals to delete node root left key. Comma key. Now, if the key is deleted is greater than the root's key, then it lies in the right subtree. So else, if key is greater than root, root right is equals to delete node root right comma key. Else, if roots dot left equals to null and root dot right is equals to null, then return null. Else, if root left equals to null, then struct node star temp is equals to root right and free root. Return temp. else if roots right is equals to null, then struct node star temp is equals to root tree root return temp. Now node with the two children get the in-order successor smallest in the right subtree. So struct node star temp is equals to min value node root right. Now we will copy the in-order successor's content to this node. So root is equals to temp. Now we will delete the in-order successor. So root right equals to delete node root right comma temp t. Now we will return root. Now let's write the main block. We will start with an empty tree struct node star root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 5 root is equals to insert root comma 3 root is equals to insert root comma 4 root is equals to insert root comma 7 and root equals to insert root comma 6. Let's try to traverse this. So cout traversal of the given tree traverse route. Now first we will delete a value. So C out, delete 2. Now root is equals to delete node root comma 2. Now C out, traversal after deleting the traverse route. Let's execute this. As you can see, we have successfully deleted 2 and traversed the tree again. Let's get back to our slides. In this session, we will talk about avial trees. We shall begin our session by what is an avial tree. Then we will discuss various rotations we can perform to balance avial trees. Then we will discuss the complexity of avial trees. After that, we will try various operations on them like insertion, deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn's YouTube channel. So let's get started with introduction to avial trees. An avial tree is a height balanced binary search tree. For each node, we have to make sure that the height of the left subtree and the right subtree can differ by at most 1. We can calculate this balance factor by subtracting the height of the left subtree from the height of the right subtree. Now let's discuss various rotations we can perform on avial trees. First up, LL rotation. Next, RR rotations. Next, LR rotation. At last, RL rotation. Let's discuss them in detail. First up, LL rotation. It is a clockwise rotation when a node is inserted on the left subtree of the left subtree of a node. Then we apply this rotation to balance the tree. It is applied on the node below the balance factor 2 node. That is, we will apply right rotation on the green node. Next, RR rotation. When a node is inserted into a right subtree of the right subtree of a node, then we perform RR rotation. It is an anti-clockwise rotation which is applied on the node below a node having balance factor -2. That is, we will apply it on the green node. Next up, LR rotation. When a node is inserted into right subtree of the left subtree of a node, then we perform LR rotation. It is a combination of RR and LL rotation. First, we will apply RR rotation on green and yellow node. After this, red node is still unbalanced, so we will perform LL rotation on the yellow node. Finally, RL rotation. When a node is inserted into the left subtree of a right subtree of a node, then we perform RL rotation. It is a combination of LL and RR rotation. First, we will apply LL rotation on green and yellow nodes. After this, the red node is still unbalanced, so we will perform RR rotation on the yellow node. Now, let's discuss complexity of avial trees. First up, space complexity is a big O of n. Next up, AVL tree offers a complexity of big O of log n for searching. Next up, AVL trees offer a complexity of big O of log n for insertion. Finally, AVL tree offers a complexity of big O of log n for deletion. We have now introduced an AVL tree and rotations on it. Now, let's discuss some of the operations we can perform on AVL trees. First up, insertion and deletion. Let's discuss them in detail. First up, insertion. We will insert a node following binary search tree rules. Then we will check if the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will create its member as public. Int key node star left node star right int height. Now let's write a function to get maximum of two integers. So int max int a comma int b. Now let's declare a utility function to get maximum of two integers. So int max a comma int b. Now let's write a function to get the height of the tree. Int height node star n. Now if n is null, then we will return 0. Else we will return n calls height. Now let's write that function to get maximum of two integers. Int max int a comma int b. We will return if a is greater than b, then we will return a, else we will return b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. Node star node equals to new node. So node key will be equals to key node left will be equals to left. Node left will be equals to null and node right will be equals to null and node height will be equals to 1. And return node. Here we have kept height as 1 because at the new node is initially added at leaf. So by default it will always be at 1. Now let's write a utility function to right rotate subtree rooted with y. Node star right node star y. Now node star x is equals to y's left and node star e2 is equals to x right. Now we will perform rotation. So x right will become y and y's left will become t2. Now we will update the heights. So y height is equals to max of height of y left comma height of y right plus 1. Now x height equals to maximum of height x left comma height of x right plus 1. Now return x. Now let's write a utility function to left rotate subtree rooted with x. So node star left rotate node star x node star y will be equals to access right and node star t2 will be equals to access vertices. Now we will perform rotation. So y left will be equals to x and x right will be equals to t2. Now let's update height. So x height is equals to maximum of height of axis left comma height of axis right and y height equals to maximum of height of y's left comma height of y's right. Return y. Now let's write a function to get balance factor of node n. So int get balance argument as node pointer n. If n is equals to null, then we will return 0. Otherwise, we will return height of n's left minus height of n's right. Now let's write a recursive function to insert a key in the subtree rooted with node and returns the new root of the subtree. So node star insert node star node comma int key. Now we will perform the normal BST insertion. So if node is equals to null, then we will return new node key. Now if this key is less than node's key, then node left will equals to insert node left comma key. or else we will insert that in the right node. Right is equals to insert node right comma key. Now we will return node. This if else will make sure that we will reach to the leaf node and then we will insert the key. Now we will update the height of this ancestor node. So node height is equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor for this ancestor node to check whether this node became unbalanced. So int balance is equals to get balance Now if this node becomes unbalanced, then there are 4 cases. So if balance is greater than 1 and key is less than node left key, then we will return right rotate node. This if statement for the left case, so or LL case. Now let's write it for the right case or RR case. So if balance is less than -1 and E is greater than node right key, then we will return left rotate node. Now write for the left right case or LR case. So if balance is greater than 1 and key is greater than node left key, then node left is equals to left rotate node left. Now return right rotate. Now let's write the right left case or RL case. So if balance is less than -1 and key is less than node to the right key, then node right will be equals to right rotate node to the right, and we will return left rotate. Now we will return this node. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root. So now if root is not null, then cout root key and now pre-order root. And pre-order. Now let's write the code for the main block. We will start with an empty tree. Node star root is equals to null. Now we will try to construct tree. So root is equals to insert root comma 10. Now root is equals to insert root comma 5. Root is equals to insert root comma 2. Root is equals to insert root comma 3. Root is equals to insert root comma 7, and root is equals to insert comma 9. Now let's try to print this tree. So cout avial tree is equals to tree in tree order. Tree order root. Let's execute this. As you can see, we have successfully created our first avial tree. Let's get back to slides. At last, deletion. We will delete a node following a binary search tree rules. Then we will check if all the nodes are balanced or not. If they are not, then we will balance it by using suitable rotations. Now let's try these operations in a code editor. Let's start by creating a node. To create a node, we need a class node. We will define its members as public int key node star left node star right int height. Now let's write a utility function to get height of the tree. So int height node star n. If n is equals to null, then in that case we will return 0. Otherwise we will return n's height. Now let's write a utility function to get maximum of two integers. Int max int a comma int b. So we will return if a is greater than b, then a, else b. Now let's write a helper function that allocates a new node with a given key and null left and right pointers. So node star new node int key. So node star new node is equals to new node parenthesis. Now new node will get key as key. New node left is equals to null and new node right is equals to null and new node's height is equals to 1 because new node is initially added as leaf. That's why it is always be given as 1. Now we will return this node. Return node. Now let's write a utility function to right rotate a subtree rooted with y. So node star right rotate node star y node star x is equals to y left node star t2 is equals to x right. Now we will perform rotation, so x right is equals to y left is equals to t2. Now we will update heights, so y height equals to maximum of height of y's left comma height of y's right plus 1 and x height is equals to maximum of height of x's left comma x's right plus 1. Now we will return this new root, so return x. Now we will write node star left rotate node star x node star y will be equals to x's right and node star t2 will be equals to y's left. Now we will perform rotation, so y left equals to x and x right is equals to t2. Now we will update these heights, so x height is equals to maximum of height of x left comma height of x right plus 1 and y's height is equals to max of height of y's left comma height of y's right plus 1. Now we will return this y. Now we will write a function to get balance factor of node n. So int get balance node star n. So if n is equals to null, then we will return 0. Otherwise, we will return height of n's left minus height of n's right. Now let's write a function to insert a node. So node star insert node star node comma int key. Now we will perform normal BST rotation. So if node is equals to null, then we will return new node key. So now if key is less than node key, then node left will be equals to insert node left comma key. Now if key is greater than node key, then node right is equals to insert node right comma key. Else we will return node because equal keys are not allowed. Now we will update the height of the ancestor node. So node height equals to 1 plus max height of node left comma height of node right. Now we will get the balance factor of this ancestor node to check whether this node becomes unbalanced. So if int balance equals to get balance of this node. Now if this node becomes unbalanced, then there are 4 cases that could be possible. First up, LL case. So if balance is greater than 1 and key is less than node left key, return, right, rotate, node. Now let's write case. So if balance is less than -1 and key is greater than node right key, then we will return left rotate node. Now let's write left right case. So if balance is greater than 1 and key is greater than node left key, then node left will be equals to left rotate node, and we will return right rotate node. Now let's write the case for right left case. If balance is less than -1 and key is less than node right, so node right is equals to right rotate node right. Now we will return left rotate node. Now let's return the unchanged node pointer. So return node. Now let's write a function to find minimum value node. So node star min value node, node star node. So node star current equals to node. So while current left is not equals to null, current is equals to current at left. Now we will return current. Now we will write a recursive function to delete a node with the given key from subtree with the given root. So node star delete node. Its arguments are node pointer root, comma, int key. For starters, we will perform standard BST delete. So if root is equals to null, then we will return root. Now, if the key to be deleted is smaller than the root key, then it lies in the left subtree. So, if key is less than root key, then root left will be equals to delete node root to the left, comma, key. Now, if key to be deleted is greater than the root key, then it lies in the right subtree. So else if key is greater than root key, then root right equals to delete node root right, comma, key. Now if the key is same as the root key, then this is the node to be deleted. So else if root left equals to null or root to the right is equals to null, then node star temp is equals to root left now if temp is equals to null, then temp will be equals to root and root will equals to null. Else root will be equals to star temp and free temp. Else node star temp is equals to min value node root right. Now we will copy the in-order successors data to this node. So root e is equals to temp key. Now we will delete this in-order successor. So root right is equals to delete node root comma temp key. Now if root is equals to null, then we will return root. Now we will update the height of the current node. So root height is equals to 1 plus max of height of roots left comma height of comma height of root right. Now we will get the balance factor of this node. So int balance is equals to get balance root. If this node becomes unbalanced, then there are 4 cases. First up, LL case. So if balance is greater than 1 and get balance of roots left is greater than equals to 0, then we will return right rotate. Now if balance is greater than 1 and get balance of root left less than 0, then root left will equals to left rotate root left. Now we will return right rotate root. Now let's write right case. So if balance less than -1 and get balance is less than equals to 0, then we will return left rotate now we will write right left case. So if balance is less than -1 and get balance of root right is greater than 0, then root right is equals to right rotate of root right. Now we will return left rotate and we will return this root. Now let's write a function to print pre-order traversal of this tree. So void pre-order node star root so if root not equals to null, then cout root e a pre-order root left and pre-order root right. Now let's write a code for the main block. We will start with an empty tree. So node root is equals to null. Now root is equals to insert root comma 2 root is equals to insert root comma 10 root is equals to insert root comma 9 root is equals to insert root comma 7 root is equals to insert root comma 5 root is equals to insert root comma 3 Now let's try and print this of AVL tree. So C out created AVL tree order tree order. Now we will delete a node. So root is equals to delete node root comma 10. Now let's again try and print this. So C out modified AVL tree order after deletion of 10. Out handle pre-order root repeat. Now let's execute this. As you can see, our deletion function is working perfectly. Now let's get back to our slides. At last, let's sum up what we have learned from this session. First up, AVL trees is a self-balancing binary search tree. Next, every node must have a balance factor of either -1, 0 or 1. Next, after every rotation, we must verify if each node is balanced or not. Finally, AVL trees offers fast insertion and deletion operations. B trees. We shall begin by introducing B trees. Then we will discuss the properties of B trees. After that, we will try various operations on them like searching, insertion and deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn. So without any further ado, let's get started with what is B tree. A B tree is a special M-way tree data structure. A B tree of order M can have at most m-1 keys and m children. Now let's discuss some properties of B trees. First up, every node in a B tree can have at most m elements. Next, every node except the root and the leaf node must have m by 2 children. Next, A root node must have at least two nodes. At last, a leaf node must be at the same level. Now, let's discuss what are the various operations we can perform on a B tree. We can perform three operations on a B tree, that is, searching, insertion, and deletion. Let's discuss these in detail. First up, searching. In this, we will traverse the complete B tree until we have found a key. We will start from the left side to go all the way up to the right side. Now, let's try this in a code editor. We will first start by creating a B tree node. To do that, we will use class B tree node int keys. It is an array of keys. Then int t. This will define the range of the number of keys. Then we will create a child pointer B tree node. See, it is an array of child pointer. Then a variable to check the current number of keys, and a boolean variable which will be true when the node is leaf. Now define some functions in public. First constructor, then a function to insert a new key in a subtree, void insert non-full, argument as int k. Next, a utility function to split the child y of the node. Argument as int I, comma, a B tree node pointer y, a function to traverse the B tree, and a function to search a key in the subtree. It will return null if key is not present. Now we will create another class B tree and make it a friend of this so that we can access private members of this B tree of this class in B tree function. Now we will create a pointer root. Minimum degree, then public, a constructor b tree, root equals to null, and t is equals to underscore t. Now we will write a function to traverse this tree. Void traverse if not null, then root traverse. Now we will write a function to search a key in this tree. Return if root is equals to null, then null, else root search. Now the main function that inserts the new key in this B tree, void insert int k. Now we will write the constructor for B tree node class. Now we will copy the given minimum degree and leaf property. Now we will allocate the memory of the maximum number of possible keys and the child pointer. And C equals to new B tree node star bracket 2 star T. Now we will initialize the number of keys as 0. Now let's write the function to traverse all node in the subtree rooted with this node. There are n keys and n plus 1 children. To traverse through n keys and first n children's, we need to do int I is for loop I is equals to 0, I less than n, I plus plus. If this is not leaf node, then before printing key, traverse the subtree rooted with child ci. So if leaf is equals to false, then c bracket I will equals to traverse, else c out case. Now we will print the subtree rooted with the last node. So if leaf is equals to false, and c I traverse Now we will write the function to search key k in subtree rooted with this node. So B tree node are B tree node search print k. We will first find the first key greater than or equal to k. So while int I is less than n and k is greater than is bracket I, then I++. Now if we found the key is equals to k, then we will return this node. If bracket I is equals to k, then we will return. If key is not found here and this is a leaf node, then if leaf is equals to true, then we will return null. Now we will try to go to the appropriate child. So we will use return c bracket I arrow search. Now we will write the main function that inserts the new key in this V tree. So void B tree insert int k. So if root is equals to null, then we will allocate the memory for root. Now root keys bracket 0 is equals to k. Now we will change root here. We are updating the number of keys in this root. Now if else if tree is not empty, then if root is full, then tree grows in height. So if root arrow n is equals to 2 star t minus 1, then we will allocate the memory for the new root b tree node star s equals to new b tree node t comma false. Now we will make the old root as child of the new root. So S arrow C bracket 0 is equals to root. Now we will split the old root and move one key to the new root. So S split child 0 comma root. Now new root has two children. We have to decide which of the two children is going to have a new key. So int I is equals to 0 if if as keys 0 is less than k. Then I plus plus and as arrow C bracket I arrow insert non full k. Now we will change the root equals to S else if root is not full we will call the insert non-full. Now we will write a function insert for non-full will initialize int I is equals to n minus 1 if if is equals to true, then while I is greater than equals to 0 and is greater than k, then keys I plus 1 will be equals to keys I and I minus minus. Now we will insert the new key at the found location. else while I is greater than equals to 0 is I is greater than k, then I minus minus. Now we will see if the found child is full. If C bracket I plus 1 L is equals to 2 star T minus 1, then we will use split child I plus 1 comma C I plus 1. Now if keys bracket I plus 1 is less than k, then I plus plus C I plus 1 insert non-full k. Now we will write the function split child y comma leaf then z and equals to t minus 1. Now for loop and j is equals to 0, j less than t minus 1, j plus plus, z equals to equals to y Now we will copy the last t children of y to z. If y leaf is equals to false, then for int j is equals to 0, j less than t, and j plus plus. Now we will repeat, now we will reduce the number of keys in y. Since this node is going to have a new child, we will create a space for the new child. So for loop int j is equals to 9, j is equals to n, j greater than equals to I plus 1, j minus minus c bracket j plus 1 equals to c bracket j. Now we will link the new child to this node. Now a key of y will move to this node and find the location of new key and move all greater keys one space ahead. Now we will increment the count of keys in this node. Now let's write the main block. We will define a B tree with minimum degree 3. Now t dot insert ten, T dot insert 20, T dot insert 5, T dot insert 6, T dot insert 12, T dot insert 30, T dot insert 7, and T dot insert 17. Now let's try to traverse this. See out. Traversal of B tree. And T dot traversal. Now let's search some keys. So let's take int k is equals to 6. So if t dot search k is not null, then cout present, else cout not present. Let's try this function one more time. With k is equals to 15. Let's execute this. As you can see, we have successfully traversed this B tree and we have checked two keys if they are present or not. The k is equals to 15 was not present and k is equals to 6 was present. Let's get back to our slides. Next up, insertion. We have to insert an element in such a way so that we won't disobey any properties of B trees. Now let's try this operation in a code editor. We will start by creating a node. To do that, we will use class bTreeNode. Then we will create an array of keys. Minimum degree, an array of child pointers, current number of keys, and a boolean variable leaf. This variable will tell if the node is leaf or not. Then we will define some public functions. We will start with constructor. Now we will create a function to insert a new key into the non-full node. A utility function to split the child. A function to traverse the tree. A friend class B tree. Now we will create this class B tree. Now we will define a pointer to root node, minimum degree, then we will create some public functions. First constructor, root equals to null and t equals to underscore t. Now void traverse now if root is not equals to null, then root arrow traverse. Now we will define a main function that inserts a new key in this B tree. Now we will write the constructor for the btree class. Int t1, comma, boolean leaf 1. Now we will copy the given minimum degree and leaf property. Now we will allocate memory of maximum number of possible keys and child pointers. Now we will initialize the number of keys as 0. Now let's write a function to traverse all nodes in the subtree. Now there are n keys and n plus 1 children, so we will traverse through n keys and first n children. So int I for loop I is equals to 0, I less than n, and I plus plus. Now suppose if this is not leaf, then before printing key, we will traverse the subtree rooted with this child. So if leaf is equals to false, then C I arrow traverse. Now we will print these keys. Now we will print the subtree rooted with the last child. So if leaf is equals to false, then Ci arrow traverse. Now we will write the main function that inserts a new key in this B tree. Void B tree int k. Now if tree is empty, then we will allocate the memory to root. So root is equals to new B tree node key, comma true. Now we will insert the key, root arrow keys equals to k, and we will update the number of keys in root. So root arrow n equals to 1. Else if tree is not empty and if root is full, then tree will grow in height. If root arrow n is equals to 2 star t minus 1, now we will allocate the memory of new root. Now we will make old root as child of new root. Is equals to root. Now we will split the old root and move one key to the new root. So to do that, we will use split child function. Zero comma root. Now new root has two children now. We have to decide which of the two children is going to have new key. So to do that, we will use int I is equals to 0 if s keys zero is less than k, then I plus plus and s arrow ci dot non-full. Now we will change the root. Else root insert non-full k. Now we will write a utility function to insert a new key in this node. We will assume the node must be non-full when this function is called. So void btree node insert non-full int k. We will initialize index as index of rightmost element. So int I is equals to n minus 1. Now if this is a leaf node, then the following loop does two things. A. Finds a location of new key to be inserted, or move all greater keys to one place ahead. So while I is greater than equals to 0 and is I is greater than k, now keys I plus 1 will be equals to keys at I and I minus minus. Now we will insert the new key at the found location. So keys at I plus 1 will be equals to k and n equals to n plus 1. Now else if this node is not leaf, then we will find the child which is going to have the new key. So while I is greater than equals to 0 and keys I is greater than k, then I minus minus. Now we will see if the found child is full. So if ci plus 1 arrow n is equals to 2 star t minus 1. Now if the child is full, then we will split it. So split child at I plus 1 comma c I plus 1. After split, the middle key of ci goes up and ci is splitted into 2. Now we will see which of the following will have the new key. If keys I plus 1 is less than k, then I plus plus c I plus 1 insert non-full k. Child int I comma a tree node. Now we will create a new node which is going to store t minus keys of y. So b tree node star z equals to new b tree node y arrow t comma y arrow leaf. Now z arrow n is equals to t minus 1. Now we will copy the last t minus 1 keys of y to z. So for loop int j is equals to 0, j less than t minus 1, j plus plus. So z arrow is j equals to y arrow is j plus t. Now we will copy the last t children of y to z. So if y leaf is false, so for int j is equals to 0, j less than t, and j plus plus, So Z Cj is equals to Y C j plus t. Now we will reduce the number of keys in Y. So Y arrow n is equals to t minus 1. Now, since the node is going to have a new child, we will create the space for the new child. So for int j is equals to n and j is greater than equals to I plus 1 and j minus minus, c j plus 1 will be equals to cj. Now we will link the new child to this node. So c bracket I plus 1 is equals to z. Now a key of y will move to this node. So we will find the location of new key and move all greater keys one space ahead. So for int j is equals to n minus 1, j greater than equals to I, j minus minus, is j plus 1 equals to is j. Now we will copy the middle key of y to this node. So keys bracket I is equals to y arrow keys at t minus 1. Now we will increment the counts of key in this node. So n equals to n plus 1. Now we will write a driver program to test above functions. Now we will write the main block. We will start with a B tree with minimum degree 3. Now we will insert keys in this tree. So t dot insert 10, t dot insert 15, t dot insert 5, t dot insert x, t dot insert 12, t dot insert 7. Now let's print this constructed tree. So see out. Created B tree S. Now T dot traverse. Now let's execute this. As we can see, we have created a B tree of order 3. Let's get back to our slides. Finally, deletion. While deleting any elements from B tree, we have to be careful not to break any properties of the B tree. Like all the leaves must be present at the same level or elements must be in ascending order. Now let's try this operation in a code editor. Let's start by creating a node. To create a node, we need a class node int star keys. This is an array of keys. Int t, a minimum degree. Now we will define an array of child pointers. So B tree node current number of keys int n, a boolean variable leaf to tell us if the node is leaf or not. Now we will define some public functions. We will start with the constructor to this class B tree node int underscore t comma boolean underscore leaf and a function to traverse the all nodes in the subrooted tree. So void traverse. Now a function to search a key in the subtree. So B tree node star search int k. This will returns null if k is not present. Now we will write a function that returns the index of the first key that is greater or equal to k. So int find key int k. Now we will write an utility function to insert a new key in this subtree rooted with this node. We will be assuming the node must be non-full when this function is called. So void insert non-full as argument as k. Now we will write a utility function to split the child of y of this node. Void split child int I, comma, b tree node star y. A wrapper function is to remove the keys k in subtree rooted with this node. So void remove int k. Another function to remove a key present in the ith position in this node, which is a known leaf node. So void remove from non-leaf int idx. Now we will write a function to get the predecessor of the key where the key is present in the idx position in the node. So int get pred int idx. Now we will write a function to get the successor of the key where the key is present in the idx position in the node. So int get successor int idx. Now we will write a function to fill up the child node present in the idx position in the C array if that child has less than t-1 keys. So void fill int idx. Now we will write another function to borrow a key from the C idx-1th node and place it in C idx node. So void borrow from rev int idx. A function to borrow a key from the idx+1th node and place it at the idx node. So void borrow from next int idx. Void merge idx. Now we will make B-tree class as friend so that we can access private members of this class in the B-tree functions. So friend class B-tree. So class will start with the pointer to the root node. So B-tree node star root int t. Now we will write some public functions. we will start with the constructor. So b tree int underscore t, so root is equals to null and t is equals to underscore t. Now a traverse function, void traverse, so we will check if root is not null, then root arrow traverse. Now we will write a function to search a key in this tree. So b tree node search int k, we will return if root is equals to null, then we will return null, else root arrow search at k. Now we will write the main function that inserts a new key in this B tree. So void insert int k. Now another main function that removes the new key in this B tree. So void remove int. Now we will write the constructor for this B tree node class. Int t1 comma bool leaf 1. So t will be equals to t1 and leaf will be equals to leaf 1. Now we will allocate memory for the maximum number of possible keys and child pointers. So keys is equals to new int bracket 2 star t minus 1 and child c is equals to new b tree node star bracket 2 star t. Now we will initialize the number of keys as 0. So n is equals to 0. Now we will write a utility function that returns the index of the first tree that is greater than or equal to k. So int b tree node find key int k. Now int idx is equals to 0. Then while idx is less than n and keys idx is less than k plus plus idx return idx. Now we will write a function to remove the key k from the tree rooted with this node. So void b tree node remove int k int idx equals to find key k. If the key to be removed is present in this node, then if idx is less than n and keys at idx is equals to k, now if node is leaf node, then we will remove from leaf node is called. Otherwise, remove from non-leaf function is called. So if leaf then remove from leaf idx else remove from non-leaf idx. Now else if this node is a leaf node, then the key is not present in the tree. So if leaf cout k is does not exist in this tree, and return The key to be removed is present in this subtree rooted with this node. The flag indicates whether the key is present in this subtree rooted with the last child of this node. So, bool flag is equals to idx equals to n if it is true, else false. If the child where the key is supposed to exist has less than t keys, then we fill that child. So if c at idx n is less than t, then fill idx. Now if flag and idx is greater than n, then c idx minus 1 remove a, else c idx remove a. Return void b tree node remove from leaf int idx. Now we will move all the keys after the idx position one place backward. So for loop int I is equals to idx plus 1, idx plus 1, I less than n, I plus I. So keys at I minus 1 should be equals to at I, and we will reduce the count of keys. So n minus minus, then return. Now we will write the function to remove the idx key from the node which is non-leaf node. So void b tree node remove from non-leaf int idx. So int k is equals to keys at idx. If the child that precedes k at CIDX has at least t keys, then we will find the predecessor pred of k in the subtree rooted at CIDX. We will replace k by predecessor recursively and delete pred in CIDX. So if CIDX arrow n is greater than equals to t, then int pred equals to get pred idx keys idx equals to pred c idx remove pred. Else if c at idx plus 1 arrow n is greater than equals to t, then int suck is equals to get suck idx. Now keys at idx is equals to suck c at idx plus 1 uses remove suck else we will merge idx and c at idx will call remove c at idx will call remove. Return. Now we will write a function to get predecessor of keys idx. So int btree node get pred int suck, repeat int idx so btree node star cur is equals to C at IDX, while cur is not a leaf, then cur will be equals to cur arrow C cur calls N. Now we will return cur key. Now we will write int b tree node get suck int idx r cur equals to C idx plus 1, while cur arrow while cur is not leaf, cur is equals to cur bracket 0. Now we will return cur Now we will write a function to fill child CIDX which has less than t minus 1 keys. Void b3 node fill int IDX if if the previous child C IDX minus 1 has more than t minus 1 keys, then we will borrow a key from that child. So if IDX is not equals to 0 and C at IDX minus 1 calls n greater than equals to t, then we will borrow from prev IDX else if IDX is not equals to n and C at IDX plus 1 calls n greater than equals to 1 t, Then we will borrow from next at idx. Else if idx is not equals to n, then we will merge idx. Else merge idx minus 1. Return. Now we will write a function borrow from prev. Tree node star child is equals to c idx tree node star sibling is equals to c idx minus 1. Now the last key from c idx minus 1 goes up to the parent, and key idx minus 1 from parent is inserted as the first key in c idx. Thus the losses sibling 1 key and child gains 1 key, moving all keys in c idx one step ahead. So for loop int I is equals to child at n minus 1 I greater than equals to 0 and I minus 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 I. Child calls keys at I plus 1 equals to child calls keys at I. Now if CIDX is not a leaf, then we'll move all its child pointers one step ahead. If underscore child calls leaf, or int I equals to child, then I greater than equals to 0, I minus minus I, child at C bracket I plus 1. equals to child C bracket I. Now we will set the child's first key equal to the key at idx minus 1 from the current node. So child is at 0 is equals to keys at idx minus 1. Now we will move siblings last child as CIDX as first child. So if child is not leaf, then child arrow C bracket 0 is equals to sibling at C sibling calls N. Now keys at idx minus 1 will be equals to sibling keys sibling calls N minus 1. Now child at N will be plus equals to 1 and sibling N will be equals to minus equals to 1. Return void B tree node borrow from next int idx. Now we will start by B tree node child is equals to C at idx and B tree node sibling is equals to C at idx plus 1. Now key IDX is inserted as the last key in the CIDX. So child keys and is equals to keys at IDX. Now child at keys X. If child is not leaf, child C equals to sibling at C0. Now the first key from sibling is inserted into key IDX. So key at IDX is equals to sibling keys 0 for loop and I is equals to 1. I less than sibling at n plus plus I sibling I minus 1 is equals to sibling now if sibling is not leaf for loop I equals to 1 less than equals to sibling calls n plus plus I calls c at I minus 1 equals to sibling calls c at I. Now we will be increasing and decreasing the key count of CIDX and CIDX plus 1 respectively. So child at n is plus equals to 1, sibling calls n minus equals to 1, return now void b tree node merge with argument as int idx b tree node star child is equals to c idx b tree node star sibling equals to c at idx plus 1. Now we will be pulling a key from the key node and inserting it at t minus 1th position in CIDX. So child calls keys t minus 1 is equals to keys at idx. Now we will be copying keys from CIDX plus 1 to CIDX at the end. So for int I is equals to 0, I less than sibling equals n and plus plus I. So child I plus t equals to sibling I. If not child calls leave for I is equals to 0, I less than equals to sibling calls plus plus I. child equals C bracket I plus T equals to sibling equals bracket I. Now for int I is equals to idx plus 1 I less than n plus I minus 1 is equals to keys at I. For int I is equals to idx plus 2 I less than equals to n and plus I c at I minus 1 is equals to c at I child n plus equals to sibling n plus 1 delete sibling return. Now we will write the main function that inserts a new key in this B tree. So void B tree int k if root is equals to null then we will allocate memory to root is equals to new B tree node t comma true root is bracket 0 is equals to k and root at n is equals to 1 else if root calls n is equals to 2 star t minus 1. So B tree node star s is equals to new B tree node t comma false. Now s c bracket 0 is equals to root s split child 0 comma root int I is equals to 0 if s keys bracket 0 less than k I plus plus s c bracket I insert non-pol k. Now we will change the root to s. Else root calls insert non-pol at k. A utility function to insert at non-full node. So int I is equals to n minus 1 if leaf equals to true. The following loop does two things: finds the location of key to be inserted or moves all greater key to one place ahead. So while I is greater than equals to 0 and keys at I are greater than k, then keys at I plus 1 will be equals to keys at I and I minus minus. Keys at I plus 1 will be equals to k and n will be equals to n plus 1. Else while I is greater than equals to 0 and keys at I is greater than k, I minus minus
F C bracket I plus 1 at n equals to 2 star t minus 1. Let child I plus 1 comma C I plus 1 F is bracket I plus 1 K I plus plus C bracket I plus 1 insert non-full K void B tree node int I comma B tree node star Y B tree node star Z is equals to new B tree node argument as Y calls T and Y calls leaf. Now Z calls N equals to T minus 1. Now we will copy the last T minus 1 keys of Y to Z. So for loop int J is equals to 0, J less than T minus 1, J plus plus. So Z keys J is equals to Y at keys J plus T. So if Y if equals to false, for int J is equals to 0, J less than T, J plus plus, J C bracket I is equals to Y calls C bracket J plus T. Now Y calls N equals to T minus 1. Now since this node is going to have a new child, we will create space for the new child. So for loop int j is equals to n, j greater than equals to I plus 1, j minus minus c bracket j plus 1 equals to c bracket j. Now c bracket I plus 1 is equals to c bracket j, c bracket I plus 1 is equals to z. Now for loop int j is equals to n minus 1, j greater than equals to I, j minus minus is bracket j plus 1 equals to keys at j is I equals to y is bracket t minus 1 n is equals to n plus 1. Now we will write function for traverse. So void b tree node traverse int I for loop I is equals to 0, I less than n, I plus plus, if leaf equals to false, then c bracket I will traverse if leaf is equals to false, then c I will call traverse function. Now we will write the function to search key in the subtree rooted with this node. So b tree node star b tree node search int k int I is equals to 0 while I is less than n ampersand k is greater than keys bracket I, so I plus plus Now if is bracket I is equals to k, then return this. Now if is equals to true, then return null. Otherwise return C bracket I calls search for k. Now we will write the utility function to remove. So void btree remove int k. If not root, then cout the tree is empty. Return. Now we will call the Now we will call the remove function for root. So root calls remove k. Now if root has 0 keys, then we will make its first child as a new root. If it has a child, otherwise set root as null. So if root n is equals to 0, then btree node star tmp equals to root. If root leaf root equals to null, else root equals to root c bracket 0. Now delete mp. Return. Now we will write the code for the main block. We will start with btree of order 3. Now let's traverse this created tree. See out, created tree. Now see out and L. Now we will use T dot remove to remove 5. Now see out, modified B tree after deleting 5. T dot traverse. As you can see, we have successfully deleted 5 from our B tree. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, all the operations on B tree have time complexities of log n. Next, all the leaves must be on the same level. Next, elements of B tree are sorted in ascending order from left to right. Finally, every node contains one more pointer than the number of elements of the node. B plus trees. We shall begin by introducing B plus trees. Then we will discuss properties of B plus trees. After that, we will try various operations on them like insertion and deletion. Finally, we will sum up what we have learned from this session. But before we begin, make sure you have subscribed to our YouTube channel and clicked on the bell icon below so you never miss an update from Simplilearn. So without any further ado, let's get started with what is a B plus tree. A B plus tree is a special m-way tree data structure. A B plus tree of order m can have at most m-1 keys and m children. A B plus tree can be used as B tree with only keys to each node and with linked leaves to which an additional level is added at the bottom. Now let's discuss some properties of B plus trees. First up, every node in B plus tree can have at most m elements. Next, every node except the root and the leaf node must have m by 2 children. Next, maximum keys for any node is m-1. And at the last, minimum keys for any node is ceiling of m by 2 minus 1. Now, let's discuss what are the various operations we can perform on B plus tree. We can perform two operations on a B plus tree. First up, insertion. Second, deletion. Now let's discuss these in detail. First up, insertion. We have to insert an element in such a way so that we won't disobey any properties of B plus trees. Now let's try this operation in a code editor. We will start by creating a node. To create a node, we need a struct B plus tree node int start data B plus tree node space star child ptr boolean leaf and int n. For the object star root will be equals to null star np pointer will be equals to null comma star x will be equals to null. Now we will write a constructor for it. So b tree node star init int I np equals to new b plus tree node np arrow data is equals to new space int bracket 5 and np child ptr is equals to new b plus tree node star bracket 6 np leaf is equals to true and np at the n is equals to 0. Now we will write a for loop I is equals to 0, I less than 6, I plus plus, np child is equals to return void traverse b plus tree node star p out and I again a for loop from I equals to 0 to I less than p at n I plus plus if p doesn't have leaf then we will traverse that child traverse p child ptr bracket I Cout, P data at I. Now we will check these conditions again for I at P at N. We will traverse it again from P child at I. Cout and L. Now next function will be used to sort this. So void sort int star P comma int N. Int I comma j comma temp for loop j equals to I, j less than equals to n, j plus plus. If p bracket I greater than p bracket j, then we will swap these two. So temp will store p at I and then p will replace its value with p at j. Now we will store the temp value in the p of j. Now let's write a function to split these child. Int split child p plus tree node star x comma int I int j mid b plus tree node star np1 comma star np3 comma star y np3 is equals to init
np3 equals to true if I is equals to -1, med is equals to x data bracket 2 x data bracket 2 will be equals to 0. Then x will store n minus minus. P1 is equals to init. Now when P1 leave will be equals to false and x leave is equals to true. So for loop j is equals to 3, j less than 5, j plus plus. J minus 3 will be equals to x data at j. np3 child ptr at j minus 3 is equals to x at child ptr bracket j np3 n plus plus x data bracket j is equals to 0. Now x greater than n minus minus. Another for loop from j is equals to 0 to j less than 6 at j plus plus rate. X child ptr at j will be stored at null. Now np1 data at 0 position will be equals to med np1 child ptr at np1 on n will be equals to x np1 child at np1 on n plus 1
will be equals to np3. np1 call n plus plus root is equals to np1. Now else y is equals to x child ptr at I and mid is equals to y at data at 2 and y on data at 2 is equals to 0. Y will store n minus minus. Now for loop j is equals to 3, j less than 5, j plus plus, np3 data j minus 3 is equals to y data j np3 n plus plus y data bracket j is equals to 0. Y n minus minus x child ptr at I plus 1 is equals to y x at child ptr I plus 1 is equals to np3 return Now we will write a function to insert into the tree void insert argument as int a so int I comma temp x is equals to root if x equals to null then root is equals to init and x will be equals to root. Otherwise, if x is leaf and x at 9, repeat, and x at n is equals to 5, then temp is equals to split child x comma minus 1 x is equals to root if a is greater than x at data at I and a is less than x at data I plus 1, I plus plus, and break. Else, if a is less than x at data 0, then break. Else, continue. X is equals to x at child at I. Else, while x leaf is false, for loop I is equals to 0 when I is less than x at n. I plus plus. If a is greater than x at data I and a is less than x on data I plus 1, I plus plus, break. else if a is less than x data break, else continue. If x child at n is equals to 5, then temp is equals to split child at x comma I x data at xn on n is equals to temp x at n plus plus continue. Else x is equals to x child ptr I x on data at x at n is equals to a sort x at data x at n x at n plus plus. Now let's write the code for the main block. First we will declare some variables as int I, n and t. Now we will request enter number of element to be inserted. In at n. Now see out. Now we will enter the element. So enter the element now we will write a for loop. So I is equals to 0 to I less than n at I plus plus. So cn t and insert
Now we will traverse this tree. So see out. Traversal of B plus tree. Traverse route. Let's execute this. We will enter 5 elements: 2, 3, 5, 7, 9. As you can see, we have successfully traversed our first B plus tree. Let's get back to our slides.
Next, deletion. While deleting any element from B plus tree, we have to be careful not to break any properties of B plus tree. Like, all the leaves must be present at the same level or elements must be in ascending order. Now let's try these operations in a code editor.
Start by creating a B plus tree. First, we will declare a global variable int max equals to 3. Then we will create a class pptree and a class node boolean is leaf int star key comma size node star ptr and a friend class pptree. Now public node variable. Now we will write class pptree so node star root void insert internal int node star comma node star. Void remove internal int comma node star comma node star. And a node function find parent node node star. Now public pptree the constructor search function. Insert function. Void remove. Void display. Star get root. E is equals to new in bracket max. Yeah, is equals to new node star bracket max plus 1. BP tree equals to null. Now void B, BP tree insert int x if root is equals to null, then root is equals to new node. Root calls key at 0 stores at xx. The root checks its leaf size is equals to 1. Else node cursor is equals to root node star parent while cursor is leaf is equals to false. parent equals to cursor now for loop int I is equals to 0 to I less than cursor size I plus plus. If x is less than cursor key at I cursor is equals to cursor at ptr at I. If I is equals to cursor size minus 1 cursor at ptr I plus 1 break. Now if cursor size is less than max, then int I is equals to 0 while x is greater than cursor key at I and then I is less than cursor size. I plus plus. For loop int is equals to cursor at size and j is greater than I, j minus minus. So cursor calls key at j is equals to cursor calls key at j minus 1. Cursor calls key at I is equals to x. Cursor calls size plus plus. Cursor calls ptr add cursor size is equals to cursor ptr add cursor size -1. Now cursor at ptr cursor size -1. Cursor ptr equals to null. Else node equals to new int virtual node max +1. For int I is equals to 0 to I less than max at the rate I plus plus. So virtual node at I is equals to cursor e at I int I is equals to 0 comma j while x is greater than virtual node bracket I is less than max I plus plus. For int j is equals to max +1 comma j is greater than
I J minus minus virtual node at J is equals to virtual node at J minus 1. So virtual node at I is equals to X. So new leaf is leaf is equals to true. Cursor size is equals to max plus 1 by 2 new leaf size is equals to max plus 1 minus max plus 1 divided by 2. Cursor bracket cursor size is equals to new leaf new leaf at new leaf size is equals to cursor ptr max. Now void bp tree insert internal int x comma node star cursor comma node star child.
if cursor size is less than max, then int is equals to 0, while x is greater than cursor at key at I and I is less than cursor of size I plus plus. For loop int j is equals to cursor size j is greater than I j minus minus cursor at key at j is equals to cursor j minus 1. Now cursor key bracket I is equals to x, cursor size plus plus, cursor at ptr bracket I plus 1 is equals to child else node star new internal is equals to new node int virtual key is max plus 1 node star virtual key at max plus 1 star virtual ptr at or int I is equals to 0, I less than max I plus plus, virtual key I is equals to cursor key for int I is equals to 0, I less than max plus 1, I plus plus. Virtual ptr I equals to cursor ptr at I. Node star pp tree find parent node star cursor comma node star child node star parent if cursor is leaf or cursor at ptr 0 is leaf. Then return null. For loop int I is equals to 0, I less than cursor size plus 1, I plus plus. If cursor ptr equals to child parent is equals to cursor return parent else parent is equals to find parent cursor ptr child. If parent not equals to null, return return parent. Now void dp tray remove int x. If root equals to null, then cout empty. Else node star cursor equals to root. Node star parent int left sibling comma right sibling. So while cursor is leaf equals to false, so for int I is equals to 0, I less than cursor size, and I plus plus. Parent is equals to cursor left sibling is equals to I minus 1, right sibling is equals to I plus 1. If x is less than cursor is
at I. Then cursor will be equals to cursor ptr. Now if I is equals to cursor size -1, equals to I, right sibling equals to I plus 2, cursor is equals to cursor ptr bracket I plus 1, break bool found is equals to false, suppose for pose equals to 0, pose is less than cursor size pose plus plus. If cursor key at pose is equals to x, then found equals to true, and then break. Now if not found, then out not return. Now if cursor size equals to 0, then cout right, delete cursor delete cursor PTR. Delete cursor. Root is equals to null. Return for loop int I is equals to cursor size equals to 0, j less than right node size I plus plus comma j plus plus cursor key at I is equals to right node cursor here add cursor size equals to null. Now see out merging 2 remove internal at right sibling -1 comma parent comma right node delete right node key right node right node. Now void tree display cursor
if cursor is not equals to null, or I equals to 1, I less than cursor size I plus plus. See out. Cursor. See out. Cursor. Key at I. See out. Handle. If cursor is leave not equals to true, and for int I equals to 0, I less than cursor size plus 1, I plus plus. Okay. Cursor ptr. Now node star bp tree get root. Return root. Now we will write the main block. We will start with an empty tree, bp tree, node. Now node dot insert 5, node dot insert 15, node dot insert 25, node dot insert 35, node dot insert 45, node dot display, node dot get root
node dot remove node dot display node dot get root. Let's execute this. As you can see, this program is working flawlessly. We have successfully deleted the key 15. Let's get back to our slides. At last, let's sum up what we have learned in this session. First up, B plus trees are fast at performing all its operations. Next, all the leaves must be present on the same level and data is only stored in the leaf node. Next, elements of the B plus tree are sorted in ascending order from the left to the right. Finally, every node contains one more pointer than the number of elements of the node.
Now with that, we have come to an end of this session on trees in data structures. If you have any queries regarding any of the topics covered in this session, or if you need the codes executed in this particular tutorial, then please feel free to let us know in the comment section below. Our team of experts will be happy to resolve all your queries. Until next time, thank you, stay safe and keep learning.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.